Okay, I've shared it maybe in the. So you can see the slides now.
Yes, yes, the slides are visible.
Okay, that's good. So can you see my first screen?
I see a slide that says control and stability of DFIG-based wind turbine systems.
Okay. So maybe we need to. Okay. So now is the first screen. So we go on with the control of the DFIG system.
Yeah, we can't access the file that you sent.
Sorry?
We can't access the file that you sent.
Why?
I think it has something to do with Aalborg. I tried to open it in the browser and sign in, but it's saying that I'm not. I don't have an email from Aalborg, so I can't access it. It might be restricted to Aalborg University.
Okay, I didn't know the real reason, but it's not a file with a password. So maybe it's through the platform. Maybe we can try to figure it out later. Okay.
Yeah, sure.
So so we go on with the courses. Okay. So in this part, I'm going to talk about the control of the DFIG-DC systems. Since in the last part we just are talking about the DFIG connected to AC grid. Here I'm going to talk about the significance of the DC grid connection for the renewable energies. As we all know that this in this figure I show the structure of a AC microgrid. We can see that for each generation, like the PV, wind, or storage, it need to use two. Since most of this kind of generation have a DC internal source inside, yes, like the PV and the wind farm, it has a DC link inside. So if you want to connect it to an AC bus, it means that you need to use additional inverters, like the DC-AC converters. So for this, that means you need to use these additional DC-AC converters, and for the load side is the same. So why do we just consider to eliminate all these additional DC-AC converter apart and just use a DC bus and to use this kind of DC microgrid? So make this comparison between the AC microgrid and the DC microgrid. We have the advantage is that first it can avoid the additional DC-AC block, and then it can reduce the system cost and complexity. Furthermore, without this additional transformation part, it can increase the system efficiency. Okay, so for the wind farm, mostly occupied by the DFIG-based wind farm. And so we are going to investigate how can the DFIG connected to the DC parts used like this, just one single AC-DC converter. And the research background is that for the conventional DFIG system, if we want to connect it to a DC link, is that we need to use additional voltage source converter like here, because for this is the conventional part. Can use a pointer. This is the conventional part, yes, just as I showed in the first slides. And this is, if we want, this is a AC side, is a alternative voltage. So if we want to change it to the DC side, we need to use a voltage source converter. And the advantage of this topology is that the control strategy is the same with the DFIG AC system. and can be easily transplanted from the existing DFIG-AC system. But the disadvantage is that it's very complex. You can see that it needs 2 converter and 1 large converter. And the capacity of the VSC is limited, like a WinGrid, which will cause some instability issues, because this VSC is the capacity is limited by the volume of the IGBT of the diode bridge, like the switches inside. So maybe why do we just here we can see there is a DC link inside of the back-to-back PWM converters. So why do we consider we directly use this DC link to connect it to our external DC bus? Okay, so like this, we make a transformation of this topology to this topology is that we call it this as like this is connected to the stator side converter. We call it as a stator side converter, not a grid side converter, since there is no grid anymore for this, no AC grid anymore for this topology. And this is still the voltage side converter. So for this topology, the advantage is that is simplified compared with this structure. And the energy transition efficiency is also improved since we didn't have one more voltage source converter and one more transformer here. So the capacity, but the disadvantage of this topology is that the capacity of the stator side stator side converter is high, since it will go through the whole power of the stator side. We know that there is a big advantage of the DFIG is that for the voltage side converter and the grid side converter is that it's only partial rated converters. It only like the occupies the 30 or % of the whole power. So that's a very significant advantage of the DFIG system. But if you change it to this topology, it will sacrifice the advantage of the converter volume, okay, capacity of the converter. So it means that why to go one step forward is that why don't we consider to use a diode bridge to substitute this stator side converter? So this is the idea. And if we use a diode bridge, we know that the diode bridge is easier to do for a high power system and without so much cost. So the advantage of using this topology is more cost effective and with a simple control structure. But the disadvantage is that since your stator side is connected to through this diode bridge, so it means that the stator side voltage will be distorted and it will cause the power and torque ripples. So that's a disadvantage of this topology. But since this topology has a very obvious advantage is that it only needs a voltage side converter, and the cost is very low, and the efficiency is also high, and the control scheme is also more simple, since only one converter needs to be controlled. You don't need to consider the collaborated control of the 2 converters, or like this is 3 converters. So there are a lot of papers doing this research, this kind of research, and we call this topology as the DFIG-DC systems. And in the later discussions and works, we are going to mainly focus on these topologies and to analyze the characteristics of this topology, and we call it as a DFIG-DC system for simplification. And so here I'm going to introduce the basic working principle of this kind of system. So first, I want to make, we can see that this is a basic diagram, and this is a DC side voltage is controlled by the other parameters connect here, because this is a DC grid. So this voltage we can assume is constant. And since we have this DC voltage here, so we can, by controlling this voltage side, to build in the exciting current here. This we call it as IR to inject into the rotor side of the DFIG. And by injecting the exciting current, we can build in the stator side voltage. You can see that this VSA, VSB, and VSC, this is the stator voltage can be established by injecting the exciting current. And since we have the stator voltage here, then with the diode bridge will be conducting. If the stator voltage is high enough, then the diode bridge conducting, and then the we can output power to the DC side. So this is a very basic operation principle of the DFIG-DC systems. And here is that we can see an equivalent circuit from the stator side. If we assume that this is the air gap, if you have some basic understanding of the DFIG models, this is the air gap side, and this is we see from the stator side, and this is the diode bridge. So from the stator side is we can see it, assume it as a sinusoidal voltage established by injecting the exciting current, and this is the stator. So this is a stator. If the diode bridge is in the 3-3 conduction mode, it means that every time at least 3 diodes are conducting. So the stator voltage will become a step wave, but the stator flux linkage is the integral of the stator voltage, so it will become less distorted. And this is a wave. So based on this wave and this working principle, we have some general questions for this topology. Firstly is that how to achieve the orientation control of the stator frequency control. Here we can see that the significant difference from the conventional DFIG-AC system is that for the DFIG-AC system, the stator is directly connected to the grid. So the SRF PL, conventional PL, can be used to obtain the orientation angle, CWPL, yes. But here is that you didn't have this idea or very good stator voltage imposed by the grid side, because since there is no grid side. So furthermore is that the stator frequency is also flexible, is also not imposed by the grid side. This is the first problem that we are encountering. Since without the stator side voltage, we can't use the conventional PL, and we didn't know what's the exact frequency of the stator side. We needed to do some extra control. And then is how to suppress the harmonic current. Since you can see that the stator voltage is distorted like this waveform, is a step waveform, so it's highly distorted. With this kind of stator voltage, we have the stator current is like this form. So how can we eliminate the harmonic currents of this kind of structure? Is also a question that we need to study. The third problem we are encountering is that how to suppress the torque ripple here. You can see that since with the highly distorted current and the distorted stator flex linkage, it's obvious that the torque will also be have a lot of torque ripples. So we needed to eliminate the torque ripples. So based on these three main problems, I have made an outline of this part of presentation. Is that the key problems we can see that the 3 problems, and the first is a robust control problem. Because I also want to introduce some control methods in this lecture. And then this is a research content and a program, and means that we needed to research in this part is for part 1. We needed to find out some methods for the stator frequency control and the how to achieve orientation control of this part, since we can't use the PL. And then is how can we suppress the torque ripple? So it's a torque ripple suppression. I have proposed some resonant controller and a repetitive controller and adaptive repetitive controller. And the third part is a harmonic current suppression. I used proposed voltage feed forward and a double axis resonant control. And for the robust control, I have proposed a coupling control method like the power current coupling control and the unified power control. So the objective of this part is I want to build a good performance and high efficiency and low cost DFIG-DC system that can be used in the real cases and application. And so first part is the stator frequency control of the DFIG-DC system. Since I just mentioned that the stator frequency is not imposed by the AC grid, since there's no AC grid for the DFIG-DC systems, because the stator side is connected to the diode bridge. Okay, so there are some papers talking about how to do the stator frequency control. And the first is that a very simple idea is that we can acquire the stator frequency. Yes, you can see from by the current model, we can acquire the stator voltage angle, and by using the differentiative of the stator voltage angle, we can get the stator frequency, and we can set a stator frequency reference and use the arrow of the stator frequency through PI controller and to get the control. And also can use control the stator frequency indirectly by controlling the angle. Since the angle, the integral of the stator frequency is the angle. So if we can control the angle to the reference value, we can have also controlled the stator frequency. But the problem of these two methods is that if we are using the stator voltage model, we can't avoid using the pure integral block. You can see here. So the pure integral block in the real application is affected by the DC offset. You can't avoid the DC sampling offset in your real applications. So this is a big problem when we are using this method. And the second is that how can we calculate the stator frequency? And if you are using the calculating frequency like this method, it has a high parameter dependency. You can see that it based on the stator flux and the voltage here. So in order to avoid these two kind of problems, I have proposed some other methods. But first, I want to introduce some operation mode of the diode bridge, since I think that if you wanted to have a better understanding of my later content, we need to have a better understanding of how the diode bridge works of this kind of structure. We can see that this is air gap electromagnetic motif, and this is the stator side resistance and leakage inductance. So the diode bridge conduction mode is determined by the ratio between the AC voltage and the DC voltage. And this is some shown of the waveforms. This is the 2-0 mode. It means that at sometimes only the two diode bridges is conducting. So there are some, and sometimes and only 0 diode bridge conducting. It means that this voltage is very small compared with this VDC. So it's the diode bridge, the current is discontinuous. You can see that this is ISA is continuous. But if you go on increasing your you can see that it's increasing the ratio between the AC voltage and the DC voltage is the 2-3-2 mode. It means that sometimes you have 2 diode conducts and sometimes 3 and sometimes 2, but it still have, when it's 2 conduct, it still have it means that one phase there low diode is conducting, so it's still have some discontinuous current. So if we go on increase the ratio between the AC side voltage and the ratio between the AC side voltage and the DC side voltage, we can see that it can achieve a 3-3 mode. It means that the current is always continuous. And based on this, since we need to make a good want to make a good utilization of this diode bridge, it means that we want to make the current to be as sinusoidal as possible. It means that we want it to be continuous. So we mainly focus on these two modes. That means that we will control the AC side voltage to large enough to make it work. And based on this, if we are working in these two main modes, we can see that there is a very, very important characteristic of these topologies, that the fundamental voltage of the stator side is equal to 2/pi VDC. And this is a very important characteristic we should keep in mind, is that since the product of the stator frequency and the flux is a constant value, if the fundamental voltage is a constant value, because the we know that the product of the stator frequency and the flux is equal to the fundamental voltage. So if the delta bridge, we can keep it always work in these two modes, we can guarantee that the product of the stator frequency and the flux is a constant value. Okay, so based on this characteristic, we can see that if we want to control the stator frequency, maybe we can just control the stator frequency flux magnitude. It's also acceptable to achieve the stator frequency control. So here, that is the method I proposed in one paper. We can see that here is in this paper, and here is that I wanted to avoid using the integral block of the voltage model to acquire the flux linkage. So I use the current model. If I use the current model, so there is no integral block without calculating the stator flux angle and without calculating the stator flux stator frequency. Just use this. If we can consider controlling the phi q is the qx stator flux to 0, it means that we can achieve a stator flux orientation on the dx side, d-axis. Okay, so it means that the main control objective is to control this to 0 phi xq, then we can achieve the orientation. And this is the indirect stator frequency control based on the flux magnitude. Since based on this orientation angle estimator, we can get the dx stator flux, and we can also get the orientation angle, and then we can do the transformation of the IR ABC in the stationary frame to the DQ frame, and then we can make it a control. That is a whole control structure. So but we can see that the drawbacks of this control method is dependent on the ratio between the stator and the mutual inductance. We can see from these slides. You need to use this parameter. So if this is have some deviations on the stator inductance or the mutual inductance, it will cause some control errors in your systems. So, and furthermore is that the control accuracy of the stator frequency is dependent on the stator flux magnitude. Sorry, I think this is a type errors. Is dependent on the stator flux magnitude, since I'm controlling the flux magnitude here. So then I may consider introduce the second method, is that maybe we can consider the stator flux PL is here, that since we notifying that we can't use the stator voltage to use for the PL, since it's highly distorted like a stable wave, but you can make a comparison of the stator flux is not so highly distorted. So why can't we consider the stator flux for the PL input, and then to use it for the acquiring the frequency and the angle? So based on this topology, we can get this is a control structure of using the direct stator frequency control method, and the details can be seen in these papers. Okay, and but the advantage is that it's still depend on the stator and the mutual inductance, since we are using the current model to acquiring the stator flux. And we can also find another ideas about acquiring the stator flux angle is by using the stator voltage model, but we didn't use the integral or using the low pass filter, but use the SOGI. You can see that if we can use a second order transfer function as a band pass filter, so we can have some good performance of acquiring the stator flux angle. And this is the control diagram. And this is the experimental setup. We can see that this rated power is 1 kilowatt, and this is the schematic diagram, and this is the experimental setup. We have a DFIG here, and we have an induction motor to serve as the prime motor to make it rotating at the rated speed. And this is controllers of the DSP controllers, and this is a diode bridge connected to the Stator side. And this is experimental results. We can see that indirect stator frequency control and the direct stator frequency can also both control the stator frequency to the rated 50 Hertz. But when we are considering some DC offset, you can see that it will have some very bad effect on the control performance. But if you can eliminate the DC offset, it will become better. So both these two methods are affected by the DC offset. It means that, and then is the during some dynamic processes, we can see that here is using the stator flux magnitude control, it will have some effect on the stator frequency during the power changes, or the torque reference changes. And here we can see that the stator flux magnitude control is affected by power changes, but the stator frequency control is not affected by the power changes. And this is using the SOGI. So since the time is not so much, so I will try to faster. And this is a performance comparison of the different frequency control method. We can see that from the different perspective, whether do you use the stator flux model or using the integral block, or do it dependent on the ratio between the stator and the mutual inductance and the sampling offset effect and the power effect. So we make a general diagram that the stator flux angle control based on the SOGI has the best performance and which is recommended based on our research. And the second part is the torque ripple suppression. We know that since the stator side is directly connected to the diode bridge, so the stator voltage is unavoidable be distorted. And if it's just slightly distorted, it means that the diode bridge working on the 2-3-2 mode. It means that there are some current discontinuous area. So the voltage is not so highly distorted. It only contains the 6th order harmonics. Here I is in the DQ frame. So the superscript 1 and 50 expresses represent the harmonic orders, and this is the harmonic frequencies. So we can see get at the stator flux and the stator current and the torque. We can see that the torque ripple as this formula, and then we can, based on this stator torque ripple, we see that is many consists of the 6th order harmonics. So we need to use a reason. Very intuitive idea is that you using a resonant controller to suppress this kind of torque harmonics. So the direct resonant control is that we, without using some other calculation processes to calculate the rotor current command, we just use the direct torque ripple arrows here, use the resonant controller and to inject it to the as a feed forward terms. So this is experimental results. We can see that using this direct resonant control, even using just only at the 6th order frequency of the resonant controller, so it can have a very good performance of eliminating the frequency of eliminating the torque ripples. Okay, and this is during the dynamic performances, and the details can be seen in this paper. And furthermore is that since the diode bridge can also works as a 3-3 mode, it means that the currents are always continuous. So the stator voltage is very highly distorted as this waveform. So it's not only just considering the 6th order harmonics, it's also consider some other high order harmonics. So this is the stator flux, and this is the stator current and the torque, experimental torque ripple. And we can see that the we needed to use a multi-resonant frequency. So I think that the repetitive controller has the characteristic. And this is the design of the improved repetitive controller. I think that due to the time limitation, I won't go to the details of how to design it, but we can see it, the difficulty is that if we are we need to achieve in the DSP controller. So we need to the discretization, and since the frequency, the harmonic frequency and the sampling frequency, the deviation between these two frequencies is not an integral. So how do we deal with the fractional delay is a problem that we need to solve. And this is some methods, and the details can also be seen in the reference papers. I want to talk it here, be seen. So, and this is the results. We can see that the improved repetitive control can suppress the torque ripples very well. And furthermore is that in some cases, we also need to consider the efficiency improvement. If we are considering the efficiency improvement, is that the Stator frequency will be have some variations during the low power mode. So we need to, if we want to design this kind of torque ripple suppressing method, we need to design an adaptive repetitive controller. And this is the details of how to design the repetitive controller. And this, I want to go to the details. And this experimental results, we can see that it works well. And the third part is about the efficiency optimization of the DFIG-DC system. And we know that the system loss is mainly considered of the copper loss and the iron loss. This is copper loss, and this is iron loss. Iron loss is considered of the hysteresis losses and the current eddy losses. Okay, so this is equivalent circuit, but the existing research is only focused on the fundamental current losses without considering the harmonic currents. So for this is that since we have make some analysis of this the characteristic of the system is that it contains a lot of harmonics. So we need to analyze what kind of harmonics have been in this kind of topology. And this is a tau equivalent circuit of the DFIG. We can get this if we don't inject the harmonic voltage from the stator side. This is harmonic current circuit without injecting the rotor harmonic voltage. And this is a calculation of the harmonic currents. We see that this is the two equations of the total harmonic currents, and this is the two figures to show the how much the harmonic currents. And we can see that both the stator and the rotor have a large contain large harmonic currents is necessary to suppress the harmonic currents. And this we can make some derivation of how to suppress the harmonic currents. And I think that a very simple idea is that since we can see it from a circuit perspective, is that if you have a distorted voltage here, if you want to suppress the harmonic current, if you don't want to have some harmonic current, and one simple idea is that you can also generate a harmonic voltage here to counteract the effect of this harmonic voltage. So this is the idea of the Stator voltage feed-forward method comes. And this is the whole control structure of the Stator sinusoidal current control strategy. And we can see that by using the Stator voltage feed-forward, the current can be more sinusoidal. And this is the dynamic processes. And furthermore is that we wanted to consider can we combine the current control and the torque ripple suppressing together to achieve a better performance. Is that we make some further analysis of how to deduce the torque ripples, and we find that the torque ripple is only related to the QX harmonic current. So it means that it leaves another freedom for the DX harmonic current control. So here we just propose a double X direct resonant control. So due to the time limitation, I didn't go to details here. We just go through this is the control diagram, and the performance analysis of double X is DX voltage control. We can analyze it through the transfer function perspective. Here is that the different transfer function. We deduce it the DX voltage, DX harmonic voltage. So it's that it has low relationship with the torque ripple. So here that maybe our idea is that we can use the QX to control the torque ripple and the DX to control the harmonic currents. So that's our ideas. Yeah. And this is the deduce of the stator harmonic voltage and the stator harmonic flux. We can see that the relationship between we use the conventional resonant control and the improved resonant control is that we can not only eliminate the torque ripples, but also can reduce the current harmonics. So this is a comparison between the loss side. And we can see that the double X can have a very good performance. Then we do some experimental for the verification. We can see that not only the current is more sinusoidal, but also the torque ripple is also suppressed. And this is the dynamic processes. And the last part is about the robust control of the DFIG-DC system. We can make here. I wanted to make a recap of the DFIG-DC system. Is that we can see that just I have introduced the working principle is that first establishing the exciting current from the water side and establishing the stator voltage. And if the diode bridge is not conducted, it's a sinusoidal voltage for the stator voltage. Yes. So if the diode bridge is totally conducted, is in the 3-3 mode, will make the stator voltage like this waveform. So it means that the main problem is how do we deal with this diode bridge? Is it a problem? And I think that from my experience, I want to share with you is that challenges and opportunities always coexist when we are doing the research. It means that we need to find the potential advantage of this diode bridge, that the stator frequency is as a degree of freedom. If you look at it from one perspective, is that you need to control it, yes. But if you look at it from the advantages perspective, is that it can be seen as a degree of freedom. You can do some other controls. And then the stator fundamental voltage is a constant, and the stator current and the stator voltage are in the same phase. You can see from this one. And this is a very, very important characteristic. I want to maybe if you want to do some further research in this area, you need to keep in mind. And this is the existing methods of the flux orientation control. I have mentioned that they have some drawbacks, but the robust control is that do we need to use the field orientation control? Is the vector control indispensable? I think that is a very important quality for us to do the research, is that we always need to think outside the box. Since for many years, when we are doing the DFIG control or the motor control, we are focusing on the orientated control or the vector control. We need to find the orientation angle and then to make a decoupling control. But here, the topology is different. We have a diode bridge here. Do we still need to think as the conventional way, or can we think it in the new way, think outside the box? Can we just make a coupling control without to be limited in the orientation angle? So that's the main idea of the later research. And based on this idea, I have proposed the coupling control method without calculating the orientation angle. And the advantage is that I can just use a directly acquired angle for avoiding avoiding the calculation of the orientation angle. Since the orientation angle is very complicated, you just see from my previous slides, and this is the waveforms is very good. And here is the power angle control methods. We don't use the stator frequency and without the stator side sensors. And then I also propose a unified control method. Just if we consider the system, it may also can work under the standalone mode. So there's a switch here. You can connect it to the DC grid. You can also work on the standalone mode. It's also based on the robust control strategy. And this is the waveforms of the experimental results. And you can see that is the change from the grid connected to the standalone. It is stable from the standalone to grid connected. It also works very well. And so the conclusion of this part is that due to the stator side diode bridge, the stator voltage and current are almost in the same phase. So which indicates that there is naturally low reactive power in the stator side. This is a very, very important characteristic we should keep in mind when we are doing research of this kind of topology. And the second is that the power magnitude and the power angle control methods are very simple and effective, which can avoid the using of stator side sensors. And this sensorless control method can improve the robustness and reliability of the DFIG-DC systems. And the unified power control strategy can make the DFIG-DC system works well in both grid connected mode and standalone mode. And this is the references. And if you want to know more details of the presentations I shown in this lecture, so you can you are referring to these references. And thank you all for the attention. And this is all from my side. And any questions or comments